Okay, so we need to do a couple of examples just so you can see that even though that might have all sound like German to you, it's really not bad. Example 1 is determine the fundamental frequency in the first three overtones for a 26 centimeter long pipe. So L is 0.26 meters. Got to change it to meters. The speed of sound is 343, so 343 meters per second in a closed tube. Okay, so we get the fundamental frequency in a closed tube by doing V, F1 is equal to V over 4L. So 343 meters per second over 0.26 meters times the 4. And when you do this, you get an F1 to be 330 hertz. Okay? And then the question says the first three overtones. So F2, F3, and F4. And in a closed tube, they are 3, 5, and 7. So the first three overtones, sorry. They're F3, F5, and F7. So times 3 times 330, 5 times 330, and 7 times 330. So 990, 1650, and 2310, all hertz. Okay, so that's the first part. Then it says in an open tube. So in an open tube, F1 is equal to V over 2L. So what was it, 343? Over 2 times 0.26. And you get an F1 to be 660 hertz. And in an open tube, all harmonics are present, so F2 will be 2 times 660. F3 will be 3 times 660. And F4. So the next three in an open tube are just 2, 3, 4. Whereas the next three in a closed tube have to be the odd ones. So this is 1320. This is 1980 hertz. And 2640 hertz. Okay, example 1. Example 2 says a vibrating tuning fork is held near the mouth of a long glass tube that is partially submerged in water. The tube is raised and the first loud sound, the first resonance point, is heard when the air column is 12 centimeters long. Okay, so our L for the first one is 12 centimeters long. If it's partially submerged in water, it means it's a closed tube, and so the first harmonic will be 1/4 of a wavelength. So L is equal to 1/4 lambda, so lambda is equal to 4 times L, and they told us the L. Lambda is equal to 4 times 0.12. So the length of the air column for the the wavelength is 0.48 meters. Okay, so continuing on, it says the room temperature is 22 degrees. And so the temperature is 22 degrees, so we can find the speed. And when you do this, you should get 343.98. Okay, saving time. I'm not showing you that. So what is the wavelength? So we found that, part A. What would the length of the air column need to be in order to hear the second and the third? So to hear the second resonating point, you're going to add a half wavelength. So L is going to be equal to 3/4 lambda. Well, we just found lambda, so we can just sub it in. So L is equal to 3/4 of 0.48. 1236. So L should be equal to 0.36 meters. This is the second length. And the third length, you're going to add another half wavelength. So it's 5 quarters. So L is equal to 5 quarters lambda, and you still know what lambda is. So sub it in, 0.48, 1260. So L is equal to 0.6. Okay, that's B. C wants to know what is the frequency of the tuning fork. So after all of that, you can do the fundamental frequency is equal to V over, and this is a closed tube, so it's 4L. So 343.98 meters per second over 4 times the original length, 4 times 12 meters. And you should get an F1 to be 716.625 hertz. Okay? One more example. Number 3. An air column opened at both ends has its first harmonic at 420 hertz. So it's an open column, and its first harmonic, F1, is 420 hertz. So the first question says, what are the frequencies of the second and the third? Too easy. Because it's opened at both ends, they're asking for F2 and F3. So 2 times F1, so 2 times 420, which should be 840. And 3 times 420, which should be 1260. Okay, part B, if the room temperature is 21 degrees, so if the temperature is 21 degrees, you can find the speed. It should be 343.39 meters per second. What is the length of the air column? So for an open tube, F1 is equal to V over 2L, which means L is equal to V over 2F1. So you're 343.39 meters per second divided by 2 times 420 hertz. And when you do this, you should get an L of 0.409 meters. Okay? So that's tubes. Hopefully they're not too bad. You'll have some practice this evening. All right, and we are now going to start light. So that's sound in a rap. And we're now going to look at the second type, specific type of wave, and that's light. And we've already said that light is an electromagnetic wave. Electromagnetic wave. That means that it does not need matter to travel. It means that it actually travels best, as in fastest, in a vacuum. Next best in air, next best in liquid, and least well in solids. Okay? And it's like you running down a hall. The hall's empty, you can go at top speed. Just like a vacuum is empty, there's no molecules that get in the way. But the more and more people in the hallway, the more you have to slow down. For light, the more and more molecules in a material, the more it has to slow down. Light is also a transverse wave. Okay, so it's one of these, okay? The type of wave that you're used to. Now, there's something called and I should tell you that physicists are a little slack. Technically, light refers to that part of the electromagnetic spectrum that is visible. But we tend to apply it to the whole electromagnetic spectrum. And I say the word electromagnetic spectrum like I'm thinking you already know what it is, but maybe you don't, so let me back up. Okay? Radiation coming from electricity and magnetism, or electrostatics and magnetism, the interaction of an electric field and a magnetic field, radiation coming from the sun, comes in a full spectrum. The visible spectrum, what we mean by the visible spectrum, would be like the rainbow. That's the visible spectrum. So the spectrum is like a whole wide range of things. So when we talk about the electromagnetic spectrum, really we're talking about all the different types of electromagnetic energy, all the different types of radiation that are present, that come from the sun and can come from other places. Visible light is just one tiny little section in here of it.